Good morning. I'm going to show you how to use curvature theory to design a 4-bar linkage. And the way we're going to do it is we're simply going to download the tool that I prepared on geogebra.org. That's this GeoGebra workbook right here. We're going to select the download the details and select download, and then agree to what GeoGebra is requiring. And what we're going to download is this file right here. Now, GeoGebra doesn't do so well when you open directly from the files. So what we're going to do is we're going to go to GeoGebra Geometry, and then we're going to open from a local file. The local files should be in our downloads, and that'll be it. This will be it right here. So we'll open that file, and what you see is a document that I've made that implements the geometric constructions in my book, Kinematic Synthesis of Mechanisms. But rather than have you execute all those constructions, I'm just going to show you how to use it. So what we have here is the moving pivot of the output link, the moving pivot of the input link, and there's nothing that really distinguishes them, but we're just going to set their color to green so you know input versus output. The triangle is the center of curvature, but for our linkage it'll actually be the physical fixed pivot. And then this point is the intersection of the ray through the moving pivot and the fixed pivot to the intersection with the inflection circle, which is green, and then the purple is the cubic of stationary curvature. We don't need these labels, and they're going to get in our way, so I'm just going to delete them. We're going to move the moving pivots around to change the shape of the 4-bar linkage and look at the associated coupler curve. So if we move these pivots around, you'll see that the center of curvature automatically moves out. It's a construction using the pole, which is the origin of the canonical frame, the intersection with the inflection circle, and the actual pivot to calculate where the curvature, where the center of curvature is. Now you're seeing the trajectory of the point coupler curve, and it is broken because the linkage itself can't move continuously through all of the positions. So the challenge here is, because when we move a pivot, we're changing the dimensions of the linkage, and the linkage may not have a rotating crank. We're going to have to move things around to find the mechanism that works. And the other thing we're going to do is we're going to be moving the coupler curve. And if we can, we want it to intersect the inflection circle, but it doesn't have to. You can actually be close to the inflection circle and still have a very large, very small, very large circle of curvature, very small curvature. We want the curvature to be near zero, so it's a straight line, but you can actually be close to it, and it's still fine. You'll notice that in this particular construction, my coupler point is always on the center of curvature. We would have to change the construction to make it a little bit more general. So here we just keep moving the two moving pivots around, and then take a look at at what the resulting curvature is. Now you see that there can be some construction challenges. This particular construction of the linkage isn't right. So let's just move it back over here. This is correct. Because you're intersecting a circle with a line, and when you're doing the construction, you have to choose one of the pivots versus the other. Sometimes the construction actually gives you a different linkage than you want. So please be patient with that. I actually have generated all the different versions, and it was too confusing. So I think we're better off just sticking with this particular one. So here we have an example of a linkage that has what seems to be a nice coupler curve. It's got a nice flat side, and then it lifts up as it comes around to engage the ground. The front and the back of the coupler curve isn't defined. You can actually, the coupler curve can move, the walking movement could be in one direction or the other. What I'm going to do now is I'm going to take a screenshot of this and then show you how to add the translating link to this 4-bar linkage to get the leg that we can use for a walking machine. So I'll be back in a minute. Good morning. It's time to show you how to construct a rectilinear moving leg from what we have constructed using the curvature theory. So let's take a look at those. I think I found it. It's in this list of screenshots. Let's see here. Here it is, here. All right, so let's copy this to Geogebra. And then I'm going to introduce a y-axis, x-axis, y equals 0 axis. And then position our system there and shrink things down just a little bit. Now I'm going to take a little bit of time generating the 4-bar linkage before I actually add the 2 links that define its rectilinear movement. So first things first, we have to add points. So this will be the ground pivot and the moving pivot of the output link, the ground pivot and the moving pivot of the input link. Now I'm going to introduce a line that I can rotate around that will be the ground link, because I'm going to need to rotate this link to position it. So I'm going to measure things from here. Let's introduce an angle. So I want to use this angle to track its movement. So I'm going to need a slider. Let's see where the sliders are. Up here. There it is, right here. So we'll put a slider in here. It'll be for an angle. We're going to want to go from 360 degrees around. Okay, and one more thing. I want not to oscillate back and forth. I want it to continue spinning. So we'll call it, say, increasing. Whoops, that was a mistake. Okay, select this. Whoops. I have to go to, we'll go here, and then we'll select animation, select settings, and here's the oscillating, increasing. All right, so now it's increasing, and we're ready to now measure. So we're going to generate a line with this angular measurement. There's alpha, and we're ready to go. it generates a point that we can now connect with a line, and I'm going to make that, I think I want to give it a color. I think I'll make it sort of a light brown, or maybe a darker brown. Yeah, that looks better to me. I'll make it thin, and when I vary the angle, it rotates the line for me. Okay, that's the line on which I'm going to build this linkage. Now you can see that this line is rotated quite a bit over, so I'm going to move it over just so I can at least visualize the linkage constructed in the same way. So now we need to measure these various links. I'm going to hide this point. I'll try to hide the points as I generate them. Okay, first thing, let's measure the base link, which goes from the moving pivot to between the two fixed pivots. Remember, the fixed pivots are the triangles here, and then we'll intersect. Okay, and now hide the circle. And I don't need this other point I. So we'll get rid of that one as well. All right. Now we do need these two lengths. So we'll generate the output link. Oh, first things first, I'm going to generate the input link, and I'm going to need the angle, the rotation angle, and that rotation angle will be from our existing line. So I'll use this angle to it. So let's create a new angle, a new slider. All right, that'll be an angle. And it will be 360, and it will be increasing. Okay, so there's our new angle. We'll introduce that here. There it is. We'll measure it from this point to this point. And that will be gamma. Okay, generate the line. And this is now the angle for our input crank. When I move gamma, it will rotate that crank. And here is the distance that defines that crank. So let's go to compass. Measure it from here to here, and then that'll be from here to here, and then we'll get the intersection. Okay, there we go. You can start hiding the things that you don't need. So let's hide K, and let's hide the circle, and we can even hide the angle delta. Let's even hide the, yes, that'll work. We can even hide the angle beta, I think. There we go. All right, so let's now introduce the segment that defines the crank, which is from here to here. I need to be able to see it, so I'm going to make it dark green and make it nice and thick. And then I'm going to hide this line and this point. Right, and now I have the crank that we're going to use to generate our linkage. We have two more this distance. We have these two distances to measure. So we'll measure the coupler. That goes at the end of the input crank, and then I'll measure the follower. That goes on the fixed pivot. And then the intersection of those two gives me the point I'm looking for. This defines the coupler now. All right, so we'll use a segment from here to here. The coupler for the coupler, and the segment from here to here is the follower. And let's give them some color. This becomes red. Make it nice and thick. Select this to be blue. Make it nice and thick. All right, and there's our linkage. We'll now hide some of these elements. Hide this. And this. All right, we can animate this. Oops, wrong one. Let's push this back to wherever we want it to be, say right about here. And we'll animate this side. Okay, let's undo the animation here. There we go. All right. And now our linkage is rotating. And now we see it move. All right, now we are going to add the coupler, and then we're going to do the construction of the other two links that form the 6-bar with the rectilinear moving link. All right, so let's stop this. All right, let's position it somewhat like what we have here. Let's now introduce the coupler point. The easiest way to do that is to measure these two angles and construct them. All right, so all right, so we'll measure the angles here. So we'll measure the angle from the moving follower pivot up to the coupler point, and then now we'll measure it, and let's see what it is so we know what it is. So that measurement is epsilon. So we'll now measure it from here. We'll go from here to here, and we'll use the make sure we're counterclockwise, and it's epsilon. All right, so now we know a line for that point that intersects the coupler curve, the coupler point. Now let's get the other one. So we'll measure the angle from the other moving pivot and up to the coupler point. And that angle, you can see now is eta. Eta is measured clockwise. So here we go. We'll go from here to here, and we want eta. And we want it clockwise. All right, so there is our line. There's our point. We'll draw the line. We intersect at our coupler point. And that now is our coupler curve. Let's hide the things we don't need. We'll hide this line, hide that angle, line of the angle. We can hide that point. So we can now introduce the polygon that defines our coupler with its coupler point. I'm going to change it to that orange color. There we go. All right, now we're in a position now to be able to animate the trajectory of the coupler point. Let's go ahead and do that. So let me stop it. Let's go to the locus. We'll select the point and we want to animate it using our crank angle. And I'm going to change its color as well. All right, so there it is. Now now we're in the position we're ready to now add the lengths that are going to provide our rectilinear leg. All right, the key step here is to measure, and we're going to construct it on the static image because it's in this particular position that we have designed the linkage. So let's just focus on this for the time being. Okay, we're going to now consider this polygon. So let's measure this polygon. And what we're going to do now is we're going to rotate this polygon the angle that we have here, DFP. So let's see, let's remember what that angle is, DFP. DFO. We want DFP. LP. Let's see, let's do it this way. I'll select it and see what it shows up. There it is. DFO. Oh, I see. P is the label that I put in there some time ago. So it's actually the point O. I didn't recognize it. All right, so that P is spurious, so this point is actually named O. So the angle that we're talking about is DFO. Here we are. So it's the angle epsilon. So what we're going to do is we're going to take this polygon and we're going to rotate it around F by the angle DFO, which is 100 epsilon. Okay, the operation we're going to use is a transform. So rotate around a point. So we're going to select that. We're going to take this polygon. Oops. Sorry, it's picking this, the entire image. So before we do that, let's reset this image. We'll put it in settings, and we'll make it a background image. There we go. All right, now it'll keep us from selecting it. Okay, we want to rotate around a point. We want to rotate this polygon around this point F, and we want to rotate by the amount epsilon. All right, we're not done. We want to now dilate it by the ratio of this length df to fp. So we want to actually expand it by whatever that amount is. So we now need to measure these two distances. So let's measure them, and then we'll dilate it by the ratio of those two. So let's measure it. All right, distance. So we want the distance between D and F, which is 2.7. See if we can move this out of the way. Okay, don't let us take it very far. Okay, and then we're going to measure FO. So measure the distance FO. That's 4.9. Drag it out of the way a little bit, however much it'll let us do. Okay, so now what we're going to do is we're going to dilate this polygon. We're going to dilate this polygon around this point. Let's see, I must not have done that correctly. Let's start up again. Okay, we're going to dilate from this point, this polygon. Yeah, so let's try that again. Okay. Dilate. Select the object. There it is. Select the center point. And now the factor. Okay. I don't know what I was going wrong before. 4.9 divided by 2.7. All right, so that's how much it's going to expand, and you'll see that it stretches out the length to the so that it expands it so that that length, which was the coupler length, is now that side of the coupler link. All right, now what? What we now do is we take what essentially what we've done is, without maybe it being obvious, we have constructed this coupler link in a position so that it is attached to the input crank. So that's actually this sort of rotation and expanding thing has positioned this link that's scaled to the original 4-bar linkage in a particular way. So we're going to now construct this link, which is basically the coupler link, on our input crank. And it uses the same two angles. I think it uses, let's see if I remember, epsilon and whatever the other one, well, it would be FDO. So I guess I erased it, but we can look, see if I can find it. Angle DFO, so there's epsilon, that's one side. And then we need DFO. I think I did epsilon too. I think it was eta, if I remember right. FDO, there it is, there's eta. So we're going to essentially use those two, and we're going to construct the coupler curve in here. So let's go ahead and do that. All right. All right, so we're going to go from this point up. So that is our DFO, which is, if you look at this, it's DFO, which is epsilon. So let's construct it. So from this point to this point, and what do we want? Epsilon. And that is counterclockwise. And there's the line. Okay, so it goes from here to here. Now we do the other side. We now go from F to E, which is the same as from F to E and back, which was our eta last time we did this. So let's go here to here. And it's clockwise now. And It's eta. Okay, it's hard to see. There it is. Okay, connect it with a line. And that is now our input crank. The input crank is essentially scaled so that it has the same geometry as the coupler, but it's scaled so that the coupler is along the input crank. That's, that sort of rotation operation that we did kind of does a lot of operations at once, and it gives us the dimensions we need. Okay, so let's hide these lines. Okay, I need. Okay, where's that line? I need Q. That line. That. We're going to get rid of G. Okay. All right, and so here is our input crank now. And we'll make it green. Oops. Make it green. So there it is. So there's our input crank. This is the new drive crank. Now the next thing we do is we come back to the static drawing, and we construct two. Let's see, we'll need to hide this. I'll have to get this out of there. All right, we're now going to construct two lines. One through P, which is parallel to this side of the rectangle, and then one through this end of the coupler point that's parallel to this side. So we'll use the parallel line, so it'll go through E parallel to this side of the polygon. All right, then we'll do the same thing through P parallel to this side of the polygon. And where those two intersect are going to be a point that we need. So let's there it is here. We'll intersect these 2 points here and here, and those are points we need. So now I'm going to go back and hide the lines. But we need these. I'm going to actually hide this as well, the distance. All right, so let's now put these segments in. The segment from, segment goes from here to here, and from here to here. Those are the two segments we need, and then we will measure those onto our moving linkage. So the first things first, compass, we go from here to here, and that fits on this point, and then we go from here to here, and that fits on this point, and they intersect in the point we are looking for. Hide the circles. Hide this one too. And introduce the two segments. These are the two new links that we're going to add to our 4-bar linkage that will provide a parallel movement. All right, so let me color them. So we'll make this one, I'll make this cyan, just to be first a different color. Let's say I'll make it cyan. Okay. And then make this one magenta. Just so. All right, now let's animate it and see what happens. Now, the construction that we're using here in effect copies the 4-bar linkage onto itself and scales it so that as the one mechanism rotates, the other mechanism kind of undoes the rotation and keeps the base link, which is this one, flat. And so it doesn't rotate. And that's why we get this rectilinear link. Now if we use our locus operation and select our point and our driving crank angle, you see that it generates exactly the same trajectory as the coupler curve. And that's really the whole point. Now let's rotate it around so that we can position the flat side of the coupler curve towards the ground. Now the next thing we have to do is we have to actually create the leg. So I'm going to do a shortcut just to give you an idea. I think there's going to be a lot more that we can do to try to get this leg mechanism correct. But let's introduce a perpendicular line between these 2 points. Oops. Sorry. Perpendicular bisector is what I wanted. There we go. All right. That wasn't right. All right. So what I want to do is I'm going to get rid of this line. Oh no, I don't want to get rid of the other line. I want to get rid of this line. That's why. All right, so let's just delete that one. Okay, there we go. I deleted the line on which I had based the entire drawing, which was not a good decision. All right, so let's do the intersection. All right, and now let's construct the leg down in this direction. Again, I'm going to sort of do a shortcut. I'm just going to take this distance. All right, and that gives me, if I intersect it, I get this point. But if I do it again, then that gives me this point down here. And so that gives me a little bit further down out of the, so it gets me a foot that is away from the moving linkage. All right, and so let's hide these circles. And let's make the foot a little bit more substantial. Let's make it a polygon. And make it magenta. I'm going to hide this line. Point, and then now we'll see what our trajectory of this point looks like. And there we are. So this now becomes our leg mechanism. It's taking a step. The whole point of this, if you remember, is so that we can change dimensions. So we should be able to sort of just vary things. Like, let's go back to our original device, and we can make small changes to it and see if there's something that we can do that's different or useful. Or maybe this point here. These are the kinds of changes that we can make. and adjust the mechanism and see how it varies with when we change different aspects of it. All right, I'm going to call it quits there. Thank you very much. I appreciate your working with me, and I hope this helps you understand how using curvature theory can help us get to one of these mechanisms with a rectilinear leg. Bye-bye.